particularly in low light settings. So in most of the CS literature, if you look at the noise models that are analyzed, or at least the assumptions that are made on whatever errors are in the measurements, typically you see that there's some kind of Gaussian assumption or boundedness assumption. In optical systems, that's not true, and that particularly becomes a problem in low light settings, where the noise is signal dependent, it's unbounded, and the variance changes from region to region across your detector. So what that means is that if you were to try to do compressed sensing with an L2, L1 type optimization problem, then you're going to have some significant challenges, because the L2 measure of data fit is going to cause some over and underfitting that you really want to avoid. So what we did is we said, well, we're going to model this noise associated with optical systems using a Poisson statistical distribution, which is very commonly used. This isn't a new idea. It's used in astronomy and medical imaging all the time. But we wanted to bound the performance of compressed sensing within this context. Okay, so the first thing we have to do is think about how to formulate the problem. And this is certainly not trivial, because within the formulation of the problem, we have to think about all the constraints inherent to optical systems. So here I've got a true intensity F star that I'm trying to estimate, and it is length M, and we're going to assume that it is strictly positive. And I here is going to denote the total amount of light available, or the total intensity of the scene. And we're going to collect N measurements. So Rich had, a length N signal and M measurements, and I just totally flipped it around to keep everybody on their toes. And what we're going to do is we're going to use or build upon what people know about Bernoulli ensembles for compressed sensing in order to construct our own compressed sensing matrix in optimal systems, in optical systems. So what you would see a lot of times in the compressed sensing literature is a sensing matrix where each element is either a plus or a minus 1 over the square root of n, where n is the number of measurements. What we're going to do is we're going to form a Bernoulli ensemble with a slightly different scaling. So each element is plus or minus 1 over n, and then we're going to take each element of that sensing matrix and add 1 over n to it, so that we can ensure every element of this new matrix A is strictly, or is greater than or equal to 0. It's certainly non-negative. And that means that we can actually think about building something like this. And in particular, the number or the amount of intensity that would be measured in this with this kind of sensing measurement or sensing matrix is roughly equal to the amount of intensity available. So we're thinking about a system here which is not somehow magically multiplying the number of photons available. So with this unusual scaling here, we're really trying to think about what's physically possible. And what we're going to assume is that we measure Poisson observations of this product A times F, and we're going to think about how to then reconstruct F from these measurements. Okay, so what we're doing is we're saying that our estimate, F hat, is going to be the minimum of not the L2, L1 objective function, but instead a negative log Poisson likelihood. So we're really going to explicitly take into account the statistics of Poisson noise plus some kind of penalty term. And that penalty term can be any number of things. It could be something that encodes sparsity. It could be a model-based thing like Rich was talking about. We're using just an information theoretic criterion on this penalty to ensure that it's valid and our proofs work out. Okay, and then we're taking into account these constraints that I mentioned earlier. So we're only going to consider positive intensity images, so no negative intensity images. And we're going to consider images with this total intensity I. Okay, and if we just take a closer look at this objective function, if we expand out that Poisson log likelihood, you can see that the intensity, or this F that we're trying to optimize over, shows up in a nice linear term here, but then it also shows up in the log, and this is kind of a challenging optimization problem that we're actively working to solve computationally. But from a theoretical standpoint, what we can show is that if you were to solve this optimization problem, then with very high probability, the error between your true scene F and your estimate F hat, and we're going to scale everything by I because we really want to bound the error between the shapes of the intensities. That's bounded by the best possible regularized L2 error in this feasible set that we're considering. So if we look again at all these positive estimators with total intensity I, and we find the one that has both a good approximation to the true intensity and if your penalty encapsulated sparsity, which has, high degree of sparsity, then our estimator has an error that's proportional to this amount here. All right. And if we wanted to think in a little bit more conventional terms about rates of error convergence, then we could make a couple of extra assumptions, like about compressibility. So if we were to assume that our true scene was compressible, so that the best k-term approximation in this compressibility matrix or basis decays like k to the minus 2 alpha, and if we were to form a penalty that basically measured the L0 norm of f, then we could show that our error, our squared error here, decays like n times log m over I to the 2 alpha over 2 alpha plus 1. And this is a very reasonable kind of error decay. In particular, one of the unique aspects is that this total intensity I shows up here. And in optical systems, the total intensity I plays the role of a signal-to-noise ratio indicator. And so as the amount of, or as the SNR increases, then our error decreases, which is what you kind of hope. And our bounds encapsulate that relationship. And if you wanted to understand this a little bit more intuitively, you could even say, well, when I've got more light, I want to have a higher resolution image, which is frequently done. So if you said, well, if I is proportional to m, and my number of measurements n is like some root of m, then you can derive your bounds and show that it's log m over m to some exponent that depends on this compressibility factor alpha and this root p that describes the relationship between the number of sensors and the number of, or the amount of resolution you want. Okay, so if we put this all together now, I've told you about two things. I told you about how in practice we can use coded aperture to get some really nice practical settings for using compressed sensing. And I've told you about how we can think about photon-limited noise and Poisson statistics in the context of compressed sensing. And one application where these things really come together is in hyperspectral imaging. So we've got some great collaborators who, well, Mike Game used to be at Duke, but is now at Arizona, and Dave Brady. And they actually built a hyperspectral imager that was measuring Bernoulli ensemble projections of each spectrum at each different spatial location. And so what we did is we took some of the data that they collected with this device, and we modeled the noise with the Poisson distribution and enforced positivity and used this L0 penalty. So we incorporated all these different constraints that I've discussed along the way here. And we used an expectation maximization algorithm to try to reconstruct the hyperspectral image. Now this is an old algorithm and certainly not the best thing that you can use for this problem. And like I said, we're actively exploring better alternatives. But at the time, this was certainly a nice kind of proof of concept of some of the principles I'm describing here today, where if we look at our observed data, you can kind of see this strange pattern on it that reflects the fact that we're making coded aperture observations of each different spectrum at each different spatial location. And if we do this reconstruction, incorporating all these constraints that I'm talking about, then we get a reconstructed total intensity, which is very accurate. And we can reconstruct the spectrum of each of the different fruits. We had orange, lemon, and lime, I think. And they match very closely to the spectra that we measure if we use a commercial kind of spectrometer. Okay, so 3 main points that I want to leave you with. First of all, coded apertures can be a very effective tool for implementing some of the compressed sensing principles that we understand in the abstract and translating them into settings where we can actually build things that are going to be useful to people. 2, that even when we've got photon noise and things are unbounded and the variance is non-uniform and we have to use this Poisson model, we can very effectively exploit sparsity and bound the performance of these kinds of optimization problems. And finally, all these ideas tie very nicely together in the context of hyperspectral imaging and yield some very promising results so far. So there's some more details and papers available on our webpage, and I just wanted to thank also some of the people who've helped support this work over the last few years. So thanks very much, and I'd be happy to answer any questions.
If there's one quick question, we could take it. Otherwise, we're going to a break right now. Are there any questions?